All right, time for another question show. Your questions, my answers, as always, wherever you are across my channel. If some question pops in your mind, whether it's about the episode we just did or just anything, just go ahead, just type it in. I'll gather them up and answer a bunch of them here. Another special guest answerer this week, a pretty cool one, an astronaut. So stick around to the end for that. All right, let's get started. Claire Hill, why does Earth spin the way it does? What would Earth be like if it spun the other way? Doesn't Venus spin the other way? If you look at the entire solar system from above, actually all the planets are doing roughly the same thing, right? The sun is turning, the planets are going around the sun, all the planets are turning, and they're all doing it in the exact same direction, except for Venus. Venus slowly turns in the opposite direction. So what this tells you, right, about all the planets and why they all spin the same way is that they all formed from the same solar nebula, and the sort of the conservation of momentum of all the individual particles averaged out, and you got this motion that everything was sort of set into place right from the beginning to sort of follow these pathways. Now, what it means, because Venus is different from the others, Venus actually turns in the opposite direction very slowly. And what that means is that at some point in the past, Venus was knocked over, literally knocked over upside down. In the way that Uranus has been rolled over onto its side, something happened to Venus in the past. If Earth was spinning in the opposite direction, and they did this in an episode of Futurama, and where they sort of spun the Earth down and then spun it up in the opposite direction, and I can't think of any reason why things would be dramatically different. The biggest difference would be, I think, that you've got the Coriolis effect. You've got sort of the direction that the storms and the currents move here on Earth, and those would be reversed. But apart from that, I don't think you would have a big change. As long as the day was about the same length, you would have life on Earth evolved, and you'd have wind, and you'd have sun and seasons and all that kind of stuff. Just things would be flipped around just because the Earth was spinning in the wrong direction. Hey Sap, they say the cosmic background radiation is the same temperature in the universe wherever you look. My question is, how come this is the case? Wouldn't the temperature be cooler near the center of the universe where it had more time to cool off? So this is kind of one of those things, right? The fact that you look in all directions and you see the cosmic microwave background radiation the same in all directions leads you to this understanding that there is no center to the universe. The Big Bang didn't happen in any one spot. The Big Bang happened everywhere. It's just an expansion. And a way to think about this is, imagine if the entire universe, sort of the three-dimensional universe in the past, was still infinite. In other words, it was infinite in all directions, up, down, right, left, forward, back, infinite. But it was more densely packed together. It was still infinite, went on forever, but it was more tightly packed together. And then the Big Bang happened, the universe stretched apart, but it was still infinite. So you had infinite but higher density, and now you have infinite and lower density. And from our position, as we look out into space and we see galaxies moving away from us, but if you go to any one of those other galaxies, you'll see galaxies moving away from you. That falls into this idea that the Big Bang is this expansion and not an explosion. And the thing is that we imagine the universe as this sort of spheres. We're kind of looking back in time as we see the cosmic microwave background. But what that really is it's a time machine. We're looking backwards in time 13.8 billion years until the point when the whole universe had cooled down to the point that light could escape. But it's not actually this sort of sphere, is not the universe. It's just our perspective from where we are here on Earth. And if we moved out to some other location billions of light years away, we would see a completely different observable universe around us. And I know it's really hard to kind of hold those two thoughts in your mind, right? On the one hand, you have sort of the objective universe that may or may not be finite or infinite, that is spreading apart. And if you could move to any other spot in the universe without having to spend the time to travel, you would see this same thing. But then to also wrap your head around as you're looking backwards in time, and the sphere that we see around us is the universe as it looked when it was younger. And these two thoughts are what cause a lot of the confusion in your brain. Derek Burge, is there a theoretical upper limit to how massive a black hole can be? Not that I'm aware of. You could put all the matter and energy in the universe, into one single black hole, and it would just be a black hole with the mass of the entire observable universe. Of course, depending on how big the universe is, maybe we know the universe is going to be much larger than the observable universe. So you could just keep gathering up more matter and just put it into a black hole. There's not some limit where a black hole just gets too full and then does something, tears open a hole in space-time and that we know of, maybe. But there really is no limit to what a black hole can do. And in fact, the more massive the black hole, the longer the black hole is going to take to evaporate and give up its mass using Hawking radiation. So if you want to kind of make the universe live the longest you possibly can, you want to gather up as much of the universe as you can into one black hole. Of course, it would be in a black hole, but it would last the longest compared to in this situation where particles are going to be, zipping away from each other. But, there doesn't seem to be any limit to how much a black hole can handle. Galley. Could a human who was born and raised on the Moon or Mars station ever live on Earth, or would they be crushed by gravity? That's a great question, and the answer is that we don't know the answer to it yet. I actually asked a similar question to this to Andy Weir when we had him on the Weekly Space Hangout a couple of weeks ago, and in his book Artemis, what he did is he sort of placed this artificial constraint, which is that no children are allowed to be born on Artemis, are allowed to be born on the Moon station because they don't know what the risks are. So the only way you're allowed to go to the Moon station is if you've already developed, you've already ended childhood, maybe you're in your early teens, and then you can go there and all your bones are grown, and then you could come back to Earth, but you would suffer gravity sickness. But right now we just don't know what the implications are, what happens to your body if you are if you gestate inside the womb in this lower gravity, if you're born and your bones develop in this lower gravity, probably won't be good. And we don't know whether it's entirely impossible for a person to ever come back to the stronger gravity of Earth. We do know that the astronauts, like Scott Kelly, was just on the International Space Station for a year, and he had a really hard time coming back to the Earth. And he's a fully grown adult and was working out nonstop on the space station, but still, when he came back, he was kind of helpless as a kitten, had a lot of difficulty in being able to just stand up and move around, and it took him weeks to kind of recover a lot of his strength. And so you can see that lower gravity of space, low gravity of Moon, low gravity of Mars, they're going to be a serious problem for any future space exploration. And we may have a situation where people can't even be born. The human body just can't handle that low gravity. So we just don't know right now what's going to happen. And it's a place where I think that we need to proceed very carefully, and we need to do experiments, and we need to just anticipate that low gravity is going to be a big problem for future colonists of Mars, and not be so reckless to just kind of go, let's all go live on Mars and then we'll just see what happens. That feels to me like it's a little too dangerous. Pandawaria. If the dark matter that surrounds a galaxy is what binds it together, does that mean that the galaxy itself would have an escape velocity based on its entire content? Yeah, absolutely. Galaxies have an escape velocity, and most of the time everything stays within the galaxy itself, but there are these situations that can kick what they call hypervelocity stars out of the galaxy. So one example of a hypervelocity event would be, say you had two stars that are in a binary pair together, and one of those stars goes supernova and disappears, and the remaining star, which was in this really tight orbit with this other star, is now sort of slingshotted outside of the galaxy. So astronomers have actually detected these stars on these escape velocity vectors. Another example is, say you could have two stars in this kind of binary system, and they get close to the supermassive black hole at the heart of the Milky Way. One star goes into the black hole, and the other one gets kicked out into this escape velocity. So there are definitely a bunch of stars that are on their way out. And so in theory, you could build a rocket that would take you on some escape velocity out of the Milky Way, but you would need to have a very, very fast rocket to be able to do it. A lot faster than anything we have today. Sergio Ortiz. Why does Canadian English sound exactly like American English with the exception of the O sound? Can you explain Hawking radiation in layman's terms? All right, I'll tackle the Canadian pronunciation first. So my wife is American and she hears it. And she says, look, we don't say oot and a boot. We say oat. So boat. This is sort of the way we sound it. So when I say, an American might say about, I hope I'm doing that right, while we as Canadians would say a boat. Although it's sort of done magnified. So obviously we don't think about it when we say it, we just say it. And but that's sort of the distinction. The one that also drives her crazy is the way I say pasta and lava. It's just like nails on a chalkboard. For her, it's pasta and lava, things like that. So there you go. That's how you can tell a Canadian is the way we say pasta. Anyway. Actually, the one that you can really tell, and the one that she catches all the time, is resources. So Americans say resources, while Canadians say resources. And so the trick is that if you're watching some television show and you see some character say resources, even though they're supposed to be an American, they're actually a Canadian actor. That's the trick. Anyway, let's get on to the second question about Hawking radiation. Now, I've done a bunch of episodes about Hawking radiation and virtual particles and all this kind of stuff, but I'll try and give you the layman's term. And the thing here, before I go into it, is what I'm going to say is pretty much wrong in that it is overly simplified and it doesn't sort of deal with this in the fields the way a proper physicist would. So the gist is that there are these virtual particles that pop into existence and then self-annihilate together. Most of the time, this is photons, right? Photons of light. So you can imagine these particles, they appear, and then they self-annihilate, they appear, they self-annihilate. And you can actually detect this by putting these plates together, and the plates will experience an outward force as these particles are appearing and disappearing in between the plates. So this stuff is actually real. And so the sort of the thought process that Stephen Hawking came up with was, well, what happens if you get these virtual particles appearing right at the edge of a black hole's event horizon? You'd have a situation where one particle would go into the black hole and the other particle would be then free to escape into the universe. And again, imagine photons is the vast majority of what these are going to be. So you're going to have a photon of light. And so if you are an outside observer and you look at the black hole, you're going to see a photon of light escape from the black hole. Now, the problem is that violates the conservation of energy. So, you can't make energy or destroy it. It can only be changed. And so in this case, a photon of energy came from the black hole, which shouldn't have been possible. And so to compensate, the black hole needs to then give up an amount of mass equivalent to E equals mc squared for that photon of light to be able to escape the black hole. And that's the gist of how Hawking radiation works. Dazanar. We haven't detected a supermassive black hole in Triangulum. I mentioned in previous episodes that every galaxy has a supermassive black hole in the middle of it, and yeah, Triangulum, which is a nearby galaxy, doesn't seem to have a supermassive black hole in the middle of it. And I said in that episode, in that question show, that the reason they don't is because they've had some kind of interaction with some other galaxy that has kicked out their black hole. And it turns out it really looks like Triangulum in the ancient past had some interaction with Andromeda. And so one of the possibilities is that Andromeda kicked out the supermassive black hole from Triangulum just in one of their interactions in the past. And it tells us that maybe in the future, when the Milky Way and Andromeda come together, that Andromeda is going to kick out our supermassive black hole, which kind of makes us feel sad, right? It's like, oh, that's our black hole, our 4.1 million times the mass of the sun monstrosity of death and destruction. Sure, it's going to destroy everything, but at least it's ours. But anyway, so it really appears that you get, through these galactic interactions, you get this rebound where the much lesser mass black hole is just booted out on an escape velocity out into deep space and never to be seen again. And so it's entirely possible that that's what happened to Triangulum and some of the other galaxies out there that don't seem to have supermassive black holes. Amateur gas. Love the moon question. What if there were two Earth-sized objects held 3 meters apart and I stood in between? My logic says that the gravity would cancel and I'd be weightless. But then again, the center of gravity would be where I'm stood and be crushed. So no, I'd be ripped in half. I don't know, help. All right, so there's a couple scenarios. You weren't entirely clear about how this was going to play out. So let's imagine you have two Earth-sized worlds and you're in between, but there's nothing holding the Earth-sized worlds. You let them go and they just mash together into one planet with double the mass of the Earth. It forms a sphere with you at the middle. But I don't think that's what you were asking. So instead, let's imagine there's two Earth-sized masses and they're being held somehow. They've got strings on the other side that are pulling them, that are stopping them from actually melding together. So yeah, you in the middle would be weightless. You would be getting pulled equally from one side to the other, and you would float and feel like you were weightless in between those two masses. Ahmed Arari. It's often stated that the magnetosphere not only shields the planet from cosmic radiation, but also prevents atmosphere loss. Why did then Venus not lose most of its atmosphere if it doesn't have a strong magnetic field? Is there another mechanism at play, or is the statement about the importance of magnetosphere to atmosphere loss prevention wrong? It's good timing, actually. Some really interesting research literally just came out. I just saw today, so I'll be able to kind of incorporate that into the answer that I give you. So yeah, from what we understand right now, Venus has no magnetosphere. Earth has the magnetosphere. Mars doesn't have a magnetosphere. The magnetosphere on Mars, likely the planet's too small, it cooled down too quickly after about 400 million years, and the magnetosphere just shut off. So that makes sense. So then the question is, why Venus, right? Venus has the same mass roughly as the Earth. It's about 90% the mass of Earth. So you'd think that it would still have a magnetosphere as well. And the thinking seems to be that at some point in the ancient past, a Mars-sized object crashed into the Earth, and this collision caused the moon to spin out. But one of the other things that it did was that because it was such a catastrophic impact, it kind of churned up and dug down deep enough to set up that dynamo effect on planet Earth. Maybe, and this is sort of the calculations, the simulations that astronomers have run, that maybe Venus didn't have a big enough impact in its ancient past to get that dynamo going, so it just never formed. Now, why does Venus have this incredibly thick atmosphere? It has an atmosphere of 93 times the atmospheric pressure of what we have here on Earth. It's because all of the carbon that would have been locked away into the rocks was released into the atmosphere. Here on Earth, most of the carbon that we have is locked away. In fact, if you released all of the carbon on Earth into the atmosphere, you would have an atmosphere of carbon dioxide, and I think it's about 50 times more mass than the atmosphere's current mass. In other words, you would multiply the current atmosphere, which is oxygen and nitrogen, you would multiply it by 50 of just carbon dioxide if you were able to release all that carbon dioxide gas out of the rocks on Earth. And so that process happened over on Venus. And so the question is, why doesn't all that carbon dioxide escape into space? And so the problem is that that Venus does have enough gravity to hold on to a heavier atmosphere, carbon dioxide. In fact, carbon dioxide, if you have carbon dioxide and you let it go, it will sink down below the oxygen atmosphere. Carbon dioxide will sink down into lower points around you. And so carbon dioxide remains in the atmosphere. The problem is that it lost all its hydrogen. The hydrogen atoms are lighter. They were the ones that were blown away. And it's the same problem that happened over on Mars. They both lost their hydrogen. And so the problem with Venus is that although it has a very thick atmosphere, it's incredibly dry. What it doesn't have is the water, which Mars does still have that water. The water's all frozen, but you could warm up the planet, you could let out all of that water, and you could then have oceans. But on Venus, this is why terraforming Venus is so much more difficult, is that there's no water there, and you would need to bring in comets from some outside source to deliver water once you had locked away all the carbon, once you'd cooled the planet down. All right, Josh Magpunk. Another question. Astronauts in orbit are not really feeling complete weightlessness, right? They're just in constant fall, like a never-ending vomit comet. What if I'm able to get out of the orbit of a body and just stop at a single point free from gravitational influences of any body? Would I experience real zero-G? And if so, where is this point? Outside the solar system? There is no place that you could go in the entire universe where you would not be under the influence of gravitational forces. You are always going to be undergoing gravitational forces. You're experiencing the gravitational force from every single object in the observable universe. Things that are, that the light left them 13.8 billion years ago, those objects, which are now further, they're 45 billion light years away, those objects, you're still experiencing the gravity from them. So you're experiencing the gravity from the computer that you're watching this on, from planet Earth, from the sun, from Mars, from Andromeda, from the Virgo supercluster, from everything. So there is no place. So then the question is, so it's about balances, right? That where could you go to a place where you're in some kind of balance from different forces? And yeah, I mean, there's all kinds of places that you could go, and you're never gonna feel anything that's different from microgravity. It's always just gonna feel like you're falling. Wherever you go, no matter what you do, you're gonna be in, whether you're far out from the solar system, as long as you're not experiencing some kind of force change. It's all about the balance of forces on your body. And so if you're not experiencing any unbalanced forces on your body, you're going to feel weightless, and it's going to feel exactly the same whether you're falling in an elevator, or whether you're orbiting the Earth, or whether you're a million miles away from any other place. Michael Murphy, do astronauts shave? How do they keep a clean face without a sink? That is a great question, and let's ask an astronaut. Astronaut Terry Virts has got an answer for you.
Hi Michael, I'm answering your question about how astronauts shave in space. I used an electric razor. Normal straight edge and shaving cream is what some guys use, but that was too much time for me. I just used an electric one on Earth, and so I used it in space. You would have to clean out the razor next to an air conditioning vent or filter so that you couldn't just dump it out in the trash can. You had to use a filter for that. And then a wet washcloth and some soap is how you would clean up. There's no showers in space, so it's basically wet towels and soap is how we stay clean, and it works out pretty good. Thanks for your question.
Thanks, Terry. That was awesome. Now, Terry just wrote a book called A View from Above, about his view from being on the International Space Station and looking down and seeing the Earth, and a lot of his photography and his experiences. So if you're interested in his point of view and his perspective, check out his book. We'll link it up. All right, well, that's it. Another question show. Thanks to everyone that sent in your questions. I really appreciate it. Special thanks to Terry Virts for jumping in and giving us a guest answer. That was awesome. How often do you get an astronaut to answer a question? That's so great. So, again, wherever you are, across my channel, some question pops into your brain, just type it in. I'll gather them up and answer them here.